Okay. Good morning. Let's start. So first, thank you for coming, because I thought maybe there's a chance that I don't have any students. I just to talk to an empty classroom today, because Monday, the earliest lecture time, and also the day before the Chinese New Year, it's a very awkward time for having class. So anyway, we'll finish today's class, and I have brought some treats for you, and we'll distribute them after class. So let's continue from last time. We did this conditional probability, which is use this notation. PE with a bar F is the conditional probability that E occurs, given that the event F has occurred. So the essence of this concept is that when some event has occurred, we are going to view that event as a new sample space and work out the events we are interested within that sample space. And mathematically, this conditional probability is computed as the probability that both E and F occurs divided the probability of this event F has occurred. And in the end of last time, we verified this conditional probability if you view it as assigning numerical values to any event in the sample space, given the assigning rule is given by this quotient defined earlier, then this function is a probability function that obeys 3 Kolmogorov axioms. So this is a valid probability function, and this means that this is other properties for probability function also automatically holds here for this kind of function, like the complement rule, sum rule, and inclusion-exclusion formulas, and many other properties. You just need to write this function in this conditional probability function way. Everything else is the same. So we'll first look at a few concrete examples to help to understand this concept. In this first example, a student is taking a 1-hour time exam. Suppose the probability that the student will finish exam in less than X hours is X half. Here X is any value between 0 and 1. Given that the student is still working after 0.75 hours, what is conditional probability that the full hour is used? Okay, to solve this one, we need the first step is to properly define the events we are going to work with. The most important information given here is the probability that the students will finish them in less than X hours is X half. So it's this probability is depending on this X variable. So it's actually sort of a function. So let's define this as an event, and this event depends on the X. So let's call it LX. I put it in the sub-index. You can also put like L parenthesis X if you prefer that way. And then L be this event. The student finished exam in less than X hours. And we are given the property of this event, property of Lx. This is X half. Here X can be any value between 0 and 1. And then let's try to denote everything else in terms of this event. So first, we are given this event that the student is still working after 0.75 hours. This means the student did not finish the exam in less than 0.75 hours. So it's the complement of this kind of event. So let's use the given event. F, that maybe I will write it in a slightly different way. The student is still working after 0.75 hours. Is the students will not finish the exam in 0.75 hours. So this event is, if you use Lx, is the complement of L. X here is 0.75. So let's just do the translation. And we are interested in finding out the conditional property that the event of the full hour is used. So let's also denote this in terms of Lx, the event that the full hour is used. So this event is the student will not finish the exam in 1 hour. So actually I should maybe denote Lx as the student will not finish the complement. It's easier. So it's we are interested in even a student will not finish the exam in 1 hour. And this is L1 complement. Okay, so what we are asked to find out is this conditional probability. The probability that the full hour is used is L1 complement, given this conditioning on this event that students still working after 0.75 hours is, as we explained, this is L 0.75 complement. That's the probability we need to find out. This is conditional probability using the definition. This is the probability of the intersection of these two events. The Y is the probability of this conditioning event. So the event behind the bar. So we are given the property Lx. To find the complement, it's just 1 minus the property Lx. And in the numerator, when you simplify this intersection of two events, and actually there is a relationship that this L1 complement is contained in this L 0.75 complement, means that this event that the student will not finish exam in 1 hour this implies that the student will not finish it in 0.75 hours. So if one event implies the other event, this means this event is contained in the other event. It's a subset of that event. So the numerator is simply just the intersection of two events, a smaller event. Okay, so now it's a quotient of these two events. By the complement rule, this is 1 minus PL1 over 1 minus PL 0.75. And PLX is half x half. So this is plugging the information given. This is 1 minus half over 1 minus 0.75 half. And simplified, we get this 0.8. Okay, so I think for this example, it's important that you properly denote the event LX or something else, your notation, and then work everything out using this event. The next example is simpler. Just go over it. The next example, a coin is flipped twice. Assume all 4 possible outcomes in the sample space containing 4 outcomes are equally likely. What is the conditional probability both flips give heads, given that the first one is the first flip give heads, the second is at least one flip gives heads. Okay, so actually there are different ways of approaching that, mentioned briefly. So for example, let's find out the conditional probability both flips gives heads. That's even B, we did not here, head. And given the first event that the first flip gives heads, so this given event is F equals head and head-tail. So if you view this F as a new sample space, look for the head within it. This is just 1/2. Or you can use their definition for conditional probability. This probability B condition F is the probability B intercept F divided probability F. This is the probability of B because B is contained in F. So it's 1/4 divided 2 quarters to get the same answer. And similar for the second part, you can use the same approach. If given the given event is at least one flip gives head, so identify this event A is head, tail, head. And so if you view this as a new sample space, you just look for the head occurs. So it's one of the 3, so it's 1/3. Or you can use the definition to write this quotient and simplify it. You get the same answer. So both approaches are correct. Okay, here's another example is similar. Here, a bin contains 25 light bulbs, of which 5 are good and function at least 30 days. 10 are partially defective and will fail in the second day of use, while the rest are totally defective and won't light up at all. Given that a randomly chosen bulb initially lights up, what is the probability that it will still be working after 1 week? Okay, so here I still just give 2 approaches. So the first one is very simple. It's like, so here we are given 25 light bulbs. 5 are good and function at least 30 days, and 10 are partially defective, but it will light up and fill in the second day use. And the remaining are totally defective, won't light up. Given that a randomly chosen bulb initially lights up, you know that this is a given event. So this means this randomly chosen bomb has to be one of the good or partial defective bombs. So if you view this as a new sample space, you have 15 outcomes in them. And we want to find the property that it will still be working after 1 week. So we want to find the chance that the chosen bomb is a good bomb. So there are 5 of them, so it's 1/3. Okay, so it's probably. So this is a method using that. So given event can be regarded as a new sample space. And if you are not comfortable with this way, you can use you can always choose the safe way is use a definition. So use a definition for conditional property and compute this quotient. It's equivalent actually. So let me here simply describe it. So let's denote the 2 events. Let me use G as this event because this is what we are interested in. The bomb is still working after 1 week. So the chosen bomb is good, meaning the good defined earlier. And then the given event, as maybe use T, is the event that the chosen bomb initially lets up. Then what we need to compute is the probability of this event G, given that event T has occurred. So it's the probability of G intersect T divided the probability of T. And also notice that G is a subset of T because even that you've chosen a good bomb, this implies it must initially let up. So it's a subset of that. This is P of G divided P of T. And probability of good bombs, there are 5 out of 25 are good bombs. And the probability that initially lets up bombs includes the good and partially defective ones. So there are 15 out of 25. You can see it's the same. Okay, so sometimes we're not just interested in computing conditional probability, but sometimes conditional probability can help us with computing the probability of intersection of 2 events. And this is called the multiplication rule. So if you have the probability of F is positive, then the probability of E intersect F is computed as the probability of E conditional F times the probability of F. So you can see the right-hand side is a multiple of these 2 events. The conditioning event, we invent this notation with the bar F. It's like a dividing F in some sense. So you multiply the probability F to cancel it, but you are left with these 2 together. So that's how you memorize that. Okay, so now we have 2 formulas. The first one is to compute the probability of union to events. You have the sum rule formula. And if you want to compute the probability of intersection to events, you can use this conditional probability. So here some explanation in words here. This formula states the probability that both E and F occurs is equal to the probability that F occurs multiplied by the conditional probability E given that F occurred. So it's used for computing the property intersection of two events. So let's see some examples. In the first example, Celine is undecided as to whether to take a French course or a chemistry course. She estimates that her probability of receiving an A grade would be 1/2 in a French course and 2/3 in a chemistry course. If Celine decides to base her decision on the flip of fair coin, what is the probability that she gets an A in chemistry? So we can first analyze what is wanted. We want to find the property that Celine takes the chemistry course and then gets an A. So it's basically can view as intersection of two events. And what is given is that the chance that the probability getting an A would be 1/2 in French course. This is translated to, given that Celine takes French course, the chance she gets an A is 1/2. And similarly, given that Celine has taken the chemistry course, the chance she gets an A is 2/3. And she decides to take French or chemistry course by flipping a fair coin. So chance she take each course is 1/2. So that's what is given. And let's use this to compute this probability. So maybe denote events. See the event that she takes chemistry. And then A is the event that she gets an A. And what we want is to compute this probability that she gets an A in chemistry. So we want to find the property intersection of this A and C. And let's see what is given, and then we integrate this into together. So we are given the probability that Celine takes the chemistry course. The probability C is 1/2, decided by flipping fair coin. And then we are given that conditioning on Celine has taken the chemistry course and she gets an A, this chance is 2/3. Okay. So you can see naturally you are going to write this as a probability A condition on C times the probability of C, because what is given here is a multiplication rule. So multiply these two numbers together, we get this is 1/3. Okay, so for this example, we know that we have to use the multiplication rule because the given information decides that, otherwise we cannot solve it. And in the following examples, we are going to work out a few examples where using the conditional property is optional. You can definitely use other methods because this is related to counting. Okay, so anyway, let's work out this together. The first example is, suppose that an urn contains 8 red balls and 4 white balls. We draw 2 balls, one at a time, from the urn without replacement. So usually we'll mention with or without replacement in drawing balls and this kind of experiment. So without replacement meaning that when you take out one ball, you will not put the select ball back into the urn. If we assume that at each draw, each ball in the urn is equal like to be chosen, what's the probability that both balls drawn are red? So we provide two solutions. The first one is using conditional property. The second one is what we are familiar is use a counting method to do that. So if we want to use conditional probability, we need to properly denote the events. Let's use R1 is the event. The first chosen ball is red. R2 is the event that the second chosen ball is red. So eventually we want to find the probability of that both balls are red. So that's intersection R1, R2. And then we want to use conditional probability, meaning we want to use the multiplication rule. So it depends on which one you want to use as this conditioning event on the right-hand side. So if things happens in order, we usually would first consider the probability of the first one occurs, and then multiply the probability of the second thing occurs given the first event has occurred. Okay. And then we figure out each probability. So the probability R1 is the first chosen ball is red. That's simple because in total we have 8 red balls and we have 8 red balls and 12 balls to choose from. So the chance of this occurring is 8/12. And then the conditional probability is that given that the first chosen ball is red, we find that the chance the second chosen ball is also red. So if the first ball is chosen, we are left with 11 balls in total to choose from. And the first ball chosen is red, so we are left with, this without replacement, we are left with 7 balls. And 7 or 11. And multiply this together, get 14/33. And the second solution is what we have been doing all the time using combinatorial analysis. Is a sample space with equally likely outcomes. So you can use the counting method. So here it depends on how you count. You just need to do it consistently. So you can, here we are going to view every ball as distinct balls, and we will not regard order of how this ball is chosen, but you can definitely consider the orders the 2 balls are chosen as matters, because here we choose 2 balls, 1 each time. You can think of, because it's without replacement, so you can sort of like taking 2 balls out at the same time. It's the same. You can count in order, but just need to count for the numerator and denominator in a consistent way. So we'll just use the number of outcomes that the 2 balls chosen are red. The y is the number of all possible outcomes. Okay, so the numerator is choose 2 balls out of 8. If we don't count in order, this binomial coefficient is to choose 2. And similarly in the denominator, choose 2 balls out of the 12 balls. We don't care about the order, it's 12 or choose 2. And of course, if you count in order, the numerator becomes 8 times 7, denominator becomes 12 times 11. So it's essentially it's the same. Okay, same answer. Okay, next let's generalize this multiplication rule. So here, if you want to find the probability of intersection of not just two events but n events, previously we have this probability A intersect B is probability A conditional on B times the probability B. And here, if we want to find the probability of the intersection n events A1 to AN, this can be written as a multiplication of these n terms. So it's PA1 times PA2 conditional A1, then PA3 conditional A1, A2, and then following this pattern, last one is the PAN conditional previous n minus 1 events occurring at the same time. So the right-hand side is the probability of the first event times the probability of the second event conditional first event occurs times the probability of the third event conditional previous two events occurs. Then I'll divide this all together. So to verify that, if you are given the formula, it's just verify these two are equal. You can start from right-hand side, use the multiplication rule. We have, the conditional probability definition, and write every conditional probability in terms of definition. You get this multiplied together, and you will see lots of cancellations. All this canceled. So the denominator is canceled with the numerator in the expression ahead of it. So in the end, you're left with one term. Another proof is like you can apply this multiplication rule for two events recursively. So this helps you to derive it. You don't need to memorize it because essentially from the non-general multiplication rule. So if you view this probability of intersection events as a probability intersection two events, you can view the intersection of the first n minus 1 event as one event. So this intersect AN by this multiplication rule. This is the probability of AN conditioning on the other events times the probability intersection of this first n minus 1 events, then apply this multiplication rule again for this intersection of n minus 1 events. You can still view it as intersection of this part intersect an minus 1 and apply that one more time. Just apply it a couple times. And then just continue this pattern. You can derive this formula. You can recover that. Okay, so let's still look at a few examples. Apply this general multiplication rule. And also here you will see this in all these examples I give you. Using the multiplication rule is optional. You can use other methods because these are kind of special examples. So here, 3 cards are selected successively at random, removed without replacement from standard deck of 52 playing cards. Calculate the probability of receiving in order a king, a queen, a jack. Okay, we'll mention 2 methods. The first one is we apply the multiplication rule, use conditional probability. The second is use counting. So if you use conditional probability, we need to define events properly. So let's let A1 is this event. The first card is king. A2 is the second card, is queen. A3 is this even, the third card is jack. And what we want is a property of A1, A2, A3. The intersection of all the three events. Okay, so if you want to use the multiplication rule, it's better to use these events in order. So it's a property of the first event times the property of the second event, given the first one has occurred. Then multiply the property of the third event occurred, given third event, given that the first two occurred. So you really apply in this way. That's how we memorize it. Okay. Then we compute each property. The property of the A1 is the first chosen card is king. So there are in total 52 cards, standing playing cards. And there are 4 of kings. That's 4 over 52. The second property is conditional property. Given that the first chosen card is king, we are left with 51 cards. And we want to choose one of the queen. There are still 4 left. Then the third conditional property is given the first 2 chosen cards are king and the queen. We want to find a chance that you have chosen a jack in the third card. So now, with the first 2 events occurred, we are left with 50 cards. And then we want to find the property that A3 occurs is there are 4 jacks left. And multiply this together. So in the exam, I prefer you just leave this answer like that. Don't need to simplify it. But if you have a calculator now, you can compute this. It's very, very small probability. And also, actually, for this one, I think it's more natural or easier for us to use accounting to solve it directly. So here we count in the order. This is a sample space with equally likely outcomes. So we just count the number outcomes of this event. First is king. Second is queen. Third is jack, and then divide the number of all possible outcomes. Just count. So here we regard the matter as matters here. So for the number of all possible outcomes, choose the first card, you have 52 choices. Second one have 51, then last one have 50 choices. Then for the numerator, the first one is king. There are 4 choices. Then the second one for queen, 4 choices. Third one, still 4 choices. Okay, let's see. Another example, maybe another 2 examples, similar kind. Then we can move on to the new topic. In this example, we have a box of fuses containing 20 fuses, 5 of which are defective. If 3 of the fuses are selected randomly and removed from the box in succession without replacement, calculate the probability that all 3 fuses are defective. Okay, so here still 2 methods. First one is use conditional property, use the multiplication rule. So let's denote the events. Let AI be the event that the nth fuse is defective. Here can be 1, 2, 3. So we are computing the probability of all three events occurring, the probability intersection A1, A2, A3. And then use the multiplication rule. Usually we apply it in terms of the order of the events. So we use this as a probability of the first event times the probability of the second event given the first event has occurred. Then the probability of the third event given the first two events have occurred. Then let's plug in the probability of these events. So probability A1 is the first chosen fuse is defective. There are 5 defective ones out of the 12. So this is quotient. Then probability A2 given A1 has occurred. Given the first chosen fuse is defective, the chance of the second one is defective is now we have left with 19 fuses. One defective one has been chosen. We are left with 4 defective ones to choose from. So 4 over 19. And similarly, the last conditional property is given the first 2 chosen fuses are defective, we are left with 18 in total fuses, and among them 3 are defective. So multiply these together. Okay, so here another approach is counting. So depends on how you count. You can think of the fuses are all distinct. And you can count in the order or does not regard order, but here let's not count in the order. Eventually it gets an answer. So if you use counting, that's just count the number of outcomes that all 3 chosen ones are defective. The wiser number of all possible outcomes. Okay. So if you don't count order, a denominator is just choose 3 fuses out of the total 20. So it's 20, choose 3. And numerator is to choose 3 defective ones. You have 5 to choose from. So you can have 5 choose 3 over 20 choose 3 equals 1 over 113. Okay, so let's look at the last one. Here we can think about it. In this one, we want to choose 6 cards at random, also result replacement from a standard deck of 52 cards. What is the probability that there will be no pairs among the 6 cards? So actually, I think it's easier to count directly using their combinatorial analysis. So let's first give this solution using their counting. And then we also mentioned that if you want to use their conditional probability, how would you do that? So this counting is we just count the number of outcomes that there's no pairs among the 6 chosen cards. And then the wide number of total possible outcomes. So here we are going to count in order. We choose each of 6 cards, which is the first one, second one, and the 6th one. So number for all possible outcomes, that's simple. It's like the first card, you have 52 choices, then 51, 50, 49, 48, then 47. So multiply these 6 numbers together. And for the numerator, we just count, we don't want any pairs. For the first card, you have 52 choices. And then for the second one, you don't want to be the same as the first card. You are left with 48 cards because there are 4 cards with the same number for each deck. And for the third card, the first 2 cards are chosen. So these 2 numbers, you don't want to have the same number. So we want to exclude 8 cards. So you're left with 44 choices. So for the first card, you are left with 40 choices if you don't want any pairs. For the next one, you are left with 36 choices, then 32 choices for the last one. Okay, so let's also solve this using a conditional property using the multiplication rule. So I think the hard part to denote the events properly. You want to write this event as a property of intersection of a few events. So we are interested in that there are no pairs in the in the 6 cards chosen. So you cannot denote an event for each card. That's not good if you want to write it as intersections. So here we are going to do this differently. We are going to denote this events AI. AI represents an event that the first I chosen cards among the 6 cards has no pairs. Okay, so you can use a conditional property to solve this one, but you need to define this events properly. So A1 is the first card, has no pair. A2 is the first 2 cards, has no pairs, like this. I equals 1, 2 to 6. Okay, so actually we are going to, so actually you can notice that A6 is the event we are interested about, and also A6 is contained in A5, it's contained in A4, contained in 2, so they have this kind of relationship. But anyway, we are going to write this property we are interested about as intersection of A1, A2 to A6. So this essentially is the same as the property A6 because they're relationship. But we intentionally write this as intersection events, so we can use this multiplication rule formula. So this is the property of the first event times the property of the second event conditioning on the first one, the property of the third event conditioning on both the first 2 occurred, then the property of the fourth event conditioning on the first 3 occurred, times the property of the 5th event conditioning on the first 4 events has occurred, then the property of the A6 last event conditioning on the first 5 events has occurred. Okay. So if you want to use conditional property, you have to do this way, and then compute the property for each of this multiple in this formula. So property A1 is there's no pair in the first chosen card. So this always holds, so it's 1, but I write it as 52 or 52. And the property A2 conditional A1, so in the first cards, no pairs, and then we want there's no pair in the first two cards. Okay, so this is just 38 over 51. Okay. You just need to choose the second card. Okay, for the property A3 contain A1, A2, so conditioning that we are given that the first 2 cards has no pair on it. So we want to find the property that there's no pair in the first 3 cards. So you just need to choose the third card, and we don't want any pair with the first 2 chosen cards. So it's 54 over 50 for choosing the third card and makes no pair with the first 2 chosen cards. And similarly, you can see we can have this each time you minus 4 in the numerator and minus 1 in the denominator. And you can have these numbers multiplied together, the same answer as if you use counting. And actually for this one, since it's more natural and easier to use counting to solve it directly. But conditional property can also be used to solve this one if you know how to use it properly. Okay, so that's the concept for conditional property, and one little application is called the multiplication rule. We can compute the probability of intersection of events using conditional property. Now let's move on to another application. This is called the total probability. So this is one of the motivation we have mentioned in the beginning of chapter 3, why we want to use conditional probability. So it can help with this kind of problem. Generally speaking, if you want to compute the probability of event B, there are applications that we can consider it under different cases. And if you are able to find a probability of B under different cases, how do we combine them together to give the probability of B? So let's consider this kind of example and derive the formula we want to present. So here we have 2 dice. We randomly choose one and roll it. We want to find the probability of this event that 3 is observed. And clearly there are 2 cases. You can either choose one die or the other, and then how to do that. So let's formulate this example into this problem and solve it together. So here we have 2 fair dice. The first die has 4 faces with numbers 1, 2, 3, 4. Second die has 6 faces with numbers 1, 2, 3, 4, 5, 6. Now we randomly choose one die and roll it, and let x be the number we get. We want to find the probability that this number x equals 3. We observe this number 3. And we can consider 2 cases and compute the probability of this event easily. The first case is the 4-face dice chosen. Then given this has occurred, the probability of x equals 3, this number is observed is 1 over 4 because it's a fair die. And also this probability we computed is actually a conditional probability. This is a conditional probability of x equals 3 given that case 1 occurs. And the second case, it can be the 6th-phase die is chosen. Then we can compute the probability x equals 3. Now it's just 1/6. And this is also a conditional probability of this event given that case 2 occurs or case 1 does not occur. So we can compute this 2 conditional probability of x equals 3 given that there are only 2 cases. So case 2 occurs means case 1 does not occur. And if we are given that, additionally, if we are given that case 1 occurs with probably half, and the other case 2 occurs must be 1 minus half is still half. Then how do we combine this together to find the probability of x equals 3? Then naturally know that. So first, we need to count in the chance case 1 occurs is half. Then multiply this conditional probability that x equals 3 given A has occurred is 1/4. And also plus, then for the second case occurs with probably half. Then multiply the probability of event occurs given this case 2 occurs is 1/6. Okay, you can see this is an average of this event. The probability of event x equals 3 occurs given that either case 1 or case 2 occurs. And if I change slightly, if I know that case 1 occurs with a probability 1/3, then case 2 occurs has to be 1 minus 1/3, 2/3. Then if you want to do this computation of x equals 3, we just need to modify these weights. So it's 1/3 times 1/4 plus 2/3 times 1/6. So it's still a weighted average of this conditional probability given that case 1 occurs or not. Okay, so what we did here is we have derived this total probability formula. The formula, it says so, if you have 2 events A and B, then the probability that B occurs can be computed as the probability of B conditional A times the probability A plus the probability of B conditional A complement times the probability A complement. So you can view this probability A and probability A complements as their little weights. We have put above 1/2 or 1/3, 2/3 because their sum equals 1. So it can be as weighted sum. And this is a useful theorem. So let me write down this in words what this means. So it says the probability of event B is equal to the weighted average of the conditional probabilities of B conditioning on either A occurs or it does not occur. Okay, so if you this explanation in words. So this is actually used for a formula in some situations we are not able to compute the probability directly, but it's easier to do the computation once we know whether another event has occurred or not. Let's also offer a simple derivation for this formula. So here we use a little lemma we have used many times. You have two events. You can create a partition of one event using the other. So we are going to write B as B, the part in A, the part in a complement. The good thing is in this decomposition, we decompose B into two parts who do not intersect each other. Then use their axiom 3, the property B equals the property of B intersect A plus the property of B intersect a complement. And once we have the property of intersection of events, we can use this multiplication rule and apply this conditional property. So the property B intersect A is the property B conditional A occurs times the property A. And similarly, we have this property B conditional A complement times the property A complement. Okay, let's see two examples to apply this formula, this total probability formula. In the first example, in answering a question on a multiple choice test, a student either knows the answer or guesses the answer at random. Let P be the probability that the student knows the answer, and 1 minus P the probability that he does not. Suppose there are m alternatives in the question. First one is what is the probability that he answers it correctly. Part B is what is the probability that student knew the answer given that he answered correctly. Okay, so let's denote some events and then work with events. So first question is we want to find out the property of this event he answered correctly. So let me use C to be the event that he answers correctly. And from what is given, that this, whether student answers correctly depends on whether he knows the answer or not. So let's denote K as the event that he knows the answer. K for no. And let's see what is given. So little p is the probability that student knows the answer. So I given the probability, given information is the probability of event k equals little p. And it's also given that the probability that a k complement is 1 minus p by the complement rule. And we are also given that if the student does not know the answer, he will guess it randomly. So we are also given this conditional probability. Given that the student does not know the answer, maybe I write here. Given that this event K complement, he does not know the answer, the chance that he answers correctly is he will guess the answer at random. He will choose one of the M choices equally likely, so this chance is 1 over M. And similarly, let's also find out the probability that the student answers correctly, given that he knows the answer. So naturally this equals 1. So if he knows the answer, he answered correctly. Okay, so part A is what is the probability that he answered correctly, and we are asked to find out the probability of C. And from what is given, and we can compute the probability of this event under different cases. He knows the answer, he doesn't know the answer. So this is a total probability formula. If you want to do a case-by-case discussion, then you can choose your total probability formula. So the formula applied directly is based on whether K occurs or not. And we can plug in the numbers now. So it's the probability C conditional on K is 1 times the probability K is P, then probability C conditional on K complement is 1 over M times 1 minus P. You can leave the answer like that, or you can maybe just sort of combine them together, or maybe do not. The answer like this is totally fine. Okay. And the second part is, what is the probability that the student knew the answer given that he answered it correctly? So let's first write this down. Probability that he knows the answer, so the probability of K conditioning on he answered correctly. So we want to find out probability K conditioning on C. Okay, so this is actually the property we are going to talk about next time. It's the Bayes theorem. So what we actually are doing here is we know that the probability that he knows the answer is P. And now we want to look for this is called the post-aware probability. Given that new information occurred, given that the student answers the question correctly, how does this change the probability of he knows the answer? Okay, so the computation is actually quite simple. Just we need to know their interpretation, what this means. So if you want to compute the conditional probability, use their definition. This is the probability of K times K intersects C over the probability of C. And in order to compute the probability of K times K intersects C, we use the multiplication rule because actually we know that in part A we have computed this, multiply this together is the intersection of C times K, C intercept K. So here we use the multiplication rule for the numerator, and then we plug in these values. So numerator is simply just 1 times P, which is P. And denominator is the probability C we compute in part A. Just put it there. So you can actually analyze this property will be bigger than P because the denominator is actually less than 1. If M is bigger or equal to 2, because if M equals 1, you get denominator equals 1, but M is usually, you have more than 2 choices. M is bigger or equal to 2, denominator less than 1. So this increases the chance that he knows the answer. Okay, so it's also intuitive because if the student answered correctly, then the chance that he knows the answer should be bigger than, so this is so-called pair probability P. So we'll talk about this kind of question next time. And for today, let's finish the last example maybe and call it a day. So in this example, let's also apply this total probability formula. An insurance company believes that the people can be divided into 2 classes, those who are accident prone and those who are not. Their statistics show that an accident prone person will have an accident at some time within a fixed 1-year period with probability 0.4, whereas the probability is only 0.2 for a non-accident prone person. If we assume that 30% of the population is accident prone, what is the probability that a new policyholder will have an accident within a year of purchasing a policy? Okay, so first let's denote the events probability. So first let's denote the event we were interested about. This is a new policyholder. We have accident within 1 year purchasing policy. Okay, so it's long. So let me use C is this event. A new, sorry about this, it's a bit long. So policyholder will have an accident within a year of purchasing policy. Okay. And we want to find the property of this event C, and it can, from what's given, you know that the probability depends on whether this person is accident prone or not. We want to do a case discussion. So let's also use another event A as event that he or she is accident prone person. And we want to compute the property of C depending on whether he's accident prone or not. So this is total probability formula. So we compute the probability as this weighted average of property of C, conditioning on it occurs or not. So let me first write down this total probability formula, and we plug in the numbers given. So let's plug in numbers. We assume that 30% of the population are accident prone. So the probability of A is 30%. Of course, the probability A complement is 1 minus 30%, the complement rule. And also this also given information that an accident prone person, given this is accident prone person, will have an accident at some time within a year, has probability 0.4. So we are given, so this is a conditional probability. If you are given this accident prone, the chance he will have an accident is 0.4. So it's our probability C condition on A. And this probability is 0.2 for non-accident prone person. So it's 0.2 for probability C condition A complement. And we multiply these given numbers together. And this is 0.26 or 26% chance. Okay, so I think that's all for today, and thanks for coming to the class despite this very special time. And I hope you have a very successful, fruitful, and healthy new year ahead. And I brought some red pockets, but no money is inside. Feel free to take one or two. Hope you have some good time for the rest of the day, even though some of you have lap time in the evening also. Anyway. Okay, so I see you guys after the new year, and have a good rest, and see you next week. So feel free to take one or two of this.